Yeah, so first I wanted to ask you, what is tactile feedback? What is your intuition about what is tactile feedback? I just wanted to go a little bit quicker, so anybody here?
There is one that you get from the device.
Okay, yep. So it is mainly the physical sensation that you feel when you interact with everyday objects. And so this can be in the form of pressure. When you press on something, it can be vibration. For example, the mobile phones, when you get a notification, it vibrates. And it can be experiencing textures, for example, a rough texture and a smooth texture. And it can also be temperature. But what we often don't think about too much is how the body itself tries to make these sensations happen in your body. So it's quite fascinating. So just underneath your skin, there is this huge network of sensors, which is called mechanoreceptors, working together as independent units, but they are responsible for creating these acting as sensors for different types of sensations. I think Anusha went through a little bit of the basis around mechanoreceptors. For example, there is Merkel cells, a type called Merkel cells that are responsible for detecting very fine edges and points, and some receptors very sensitive to high frequency, like very high frequency vibrations, and some of them are responsible for skin stretch. And so what Vibro-tactile does here is it uses these mechanical actuators that addresses the vibration part of this sensation that we have. So there are actuators that are placed on our skin surface that oscillates at different frequencies so that you can feel these vibrations. And so this is a simple demonstration of how Vibro-tactile actuators work. So there are these different types of actuators that are placed on the skin surface. As you can see, they are quite small, but they are very small. There's still some mechanical component into it that creates these vibrations. And there are different types of mechanical actuators. I think I want to skim this through because Anusha gave a brief about it as well. Different types, for example, eccentric rotation motors, linear resonant actuators. And also, if you have seen these large, huge speakers, when they work under very high intensity volume, they go up and down. That's sort of the technology that is used in the voice coils. And also there is a technology called piezoelectric actuators that can create very high frequency sort of vibrations. So these are the main actuator family that is behind Vibro-tactile technology. And when you go into applications, for example, in virtual reality, if you get the Quest headset, you have the controllers with Vibro-tactile feedback. If you get a smart ring, you have Vibro-tactile feedback. Obviously, the mobile phones and your smartwatch gives you notifications with vibrations, and haptic gloves as well. And so what we are focusing today mainly, one of the areas we want to focus is how can you get into this technology and prototype with it. So that is where this toolkit Vibra-Forge comes. So it is a toolkit that is developed so that everybody, a novice designer who's not too much into technology, is abstracted from that particular level, and you can completely focus on the top level, integrate them into, for example, this is an example of having these Vibro-tactile actuators, very modular. It can be scaled. You can scale up to about 128 actuators and put them on your sleeves and experience this technology. And it is not limited. So for example, you can work with one actuator, two, and it can go up to 128, which is customizable. And so this work was done by Binjiang Huang. And so this is it's a completely open source toolkit. So it has support for Unity as well, where you'll be integrating this Vibro-tactile technology when you're working in the VR. So I've attached the QR code. Please feel free to visit and get access to the GitHub so you have the resources when you're working within this week. Yeah, so these are some of the enabling applications demonstrated by the team for the Vibro-tactile toolkit. For example, phonemic displays where they tried to map audio into vibration, basically tactile sensations, and a VR fitness app, and also drone teleoperation. And as always, so we talked about some of the advantages of these technologies. There are also limitations if you saw in these technologies. Even though they try to make it scalable, you still see these individual actuators that can be mechanically bulky. So to get some higher resolution tactile feedback, you need to have one motor, one particular unit at each point to get this resolution, which is still a mechanical component that is hanging on your body. And so the amount of the diversity of sensations that you can create from vibro-tactile feedback is actually limited. Also, as I said before, the coarse spatial detail, so it's harder to render fine texture details. For example, practically, if something is vibrating on your body, it's very hard to have another vibration unit close to it because the vibration spreads around. It is not something very localized. It is spread around a mechanical, physical object. And there is always this technical aspect of latency. For example, when you're dealing with very time-critical tasks, for example, interactions in virtual reality, and our human senses are super fast, but they're mostly within these limits of not being able to discriminate. But at times, these actuators can have latencies. For example, you give the signal, but there is a latency that actually the output happens. So that is one of the challenges in the technology. Yeah, so that is a bit about the vibro-tactile technology and the vibro-tactile toolkit, which is Vibro-Forge, and what it enables. And now that we looked into this particular slide before, which is the electrical system of our bodies and the network of sensors. So how actually this works is, these sensors that I talked about before are actually sensitive to mechanical disturbances. For example, to feel pressure, your skin should be mechanically or physically pressed so that it gets deformed, and these sensors give an electrical signal that is transported through these nerves to your brain. So it's quite fascinating how these different sensor networks or the mechanoreceptors work. When you touch or when you interact with a physical object, what happens is these nerve endings called the mechanoreceptors creates these electrical signals that are traversed through the nervous system into your brain. And then the brain decodes these as different sensations. And so the question that we wanted to ask here was, can we hack into this system? If this is an electrical network, can we sort of give these electrical signals externally and hack into this, the electrical system of our body? And this is exactly what a technology called electro-tactile does. So instead of having a physical disturbance externally, we use no mechanical actuator, but a set of electrodes that can give you an electrical pulse externally from the skin, so that these electrical pulses will go to our skin and excite these nerve fibers. So there won't be any mechanical motor or something like we saw in vibro-tactile that creates vibration, but it's a set of electrical pulses carefully controlled in terms of time and in terms of frequency, etc. So there will be electrode interfaces that directly stimulate these nerves, and these electrical signals will be traversed through our nervous system to the brain, and brain gets tricked through representing them as some sort of tactile sensation. For example, most commonly it can be tingling, and at times there are some interesting sensations as well, which I will come up to later. And So now I want to look at why this technology is actually interesting in its core. So one of the main reasons is, as I said, there are no mechanical actuators. As my initial said before, one of his previous work was Tactile, which is a very thin and conformal actuators on your skin. So if you can see, this is a very thin actuator that is placed on your body, which you can feel the tactile sensation, and also it tries not to obstruct the natural sensations. You can still interact with the physical world, but also feel this augmented tactile feedback on top of what you feel in the real world. And also, because it is electrical system, it can be used in rapid fabrication like 3D printing. You have the luxury now of using multi-material 3D printing, very accessible. So you can use these conductive and unconductive materials to have these traces fabricated in 3D interfaces, create tactile feedback interfaces using 3D printing. And also there is some exciting research that has been recently done so that you can have fully unobstructed virtual reality experiences. So this is about bringing in sensations. When you actuate your hands from the back of it, you feel the tactile sensations on the front of it. I don't want to go into technical details, but this all comes given the fact that we can manipulate the electrical system of the body, which is interesting. You can go and do a bit of more search. And also there are some interesting sensations other than tactile feedback itself. For example, Kajimoto in 2021, they presented a system in the forehead where you can render thermal feedback using electrical stimulation. That itself, as I said before, there are an abundant amount of thermal receptors that are accessible in our foreheads. When we electrically stimulate them, you feel this effect of thermal sensation. And also some tactile illusions like compliance. So you can check these work out. But one of the things about the technology itself was because it is electricity, there are some challenges that are involved with the technology. You need very high voltages in order to overcome the barrier of the skin impedances. And so there is a high barrier to entry. And because this barrier, so people who want to get into electro-tactile would focus more on developing the hardware and getting the hardware resources, so it hinders the design exploration. And also some of the systems that are existing might be customized to particular applications. So the requirements of applications changes from application to application. So it's very hard to scale the systems. And always electricity is electricity. We cannot change physics, but because of these inherent requirements of these systems, there are some safety and calibration concerns. So this is where one of my major research comes in. It's the toolkit that we developed with Anisha and Ramidu here. So it is eTactile kit. So where you can prototype electro-tactile in a safer and a faster way. So you can make it scalable, you can make it more accessible. So you don't need to focus on this difficulty in getting into the hardware. We got that covered for you so that you can design on top of that. So we have support for creating spatial tactile patterns with easy tools, and also you have access to APIs for popular platforms like Python and Unity, and quickly script them out. And yeah, so that's, and so you'll be having access to the toolkit. I'm quite happy for you to try it out today while we are here when you're getting started. And also we have it fully open sourced, and so that's what you'll be going to use. So you can scan the QR code, access it through our GitHub. So we have the Unity APIs built for you. Hopefully you can get started pretty quickly with that. And with this particular toolkit, and I wanted to talk about one of the applications, or like one of the main projects that we did very recently with my colleague, Ihao, who's back from the School of Computer Science. So, so this project was stack deformed. trying to render virtual geometry in virtual reality. If you can see, one of the advantages of electro-tactile itself, as I said before, is the higher resolution. You cannot have, so this particular project, we use a grade of 32 electrodes on your index fingertip, which is practically not possible with Vibro-tactile. And so what we used in this was an analogy. When you interact with physical objects in the practical world, so a part of healing the object is that how your fingertips gets deformed. So we tried to map that deformation, how the fingers would deform when we interact with virtual reality, practical physical objects into virtual reality through tactile patterns, which help us to render, which helps people to map these sensations or tactile patterns into virtual elements. So this is a short video of it. So we were able to render edges, faces, and corners with tactile patterns that emulate how our fingers would deform practically. I'm sorry about the lag because it's going through Zoom and coming here. So the videos are not quite continuous, but I hope you get the gist of it. Yeah, so given that we were talking about the strength, sorry, this should be electro-tactile. So it has high resolution. There are no bulky actuators, and it's very fast because it's electrically controlled, and it's we have this very fast running hardware. So it's there's no middleman in between that gets the feedback to you. We directly give these electrical pulses that are sent to your skin, so we can control it very fast. And there's a broad amount of sensations other than the vibration itself, as I showed before. But given that the systems come with limitations itself. So one of the major limitations that we are also working on currently is, so electro-tactile needs calibration individually and over time. So even for a person who calibrates, which calibration means, let's say, the intensity. So a person who got calibrated, okay, so now you can feel the sensation, but another person who tries the same system when it's activated might not feel it, and in the worst case, it might be painful as well. So that is one thing that we want to look into, how we can generalize this system so that any person can quickly use it. For example, your mobile phones, the vibration of the haptics that comes, it doesn't have these intensities, but almost all the people can feel it. So that is one of the things that we are looking in this electro-tactile technology. And also there are things like electrode degradation, because we use contact with electrodes. For example, our skin can get sweaty, and because these are conductive elements that will interact with the chemicals in our sweat, they can degrade over time. And so even though our toolkit manages safety and everything, I just want to give you a warning. So as I said, so this is within a safe range. If you can make it unpleasant if you want to, but we have done our best to keep it within the safe ranges. So it is safer, but we can make it unpleasant if you want to. So keep that in mind when you're using the toolkits. Yeah. So now that I've given a brief about the toolkits, I want to put some areas or seed some of the thoughts that I had in mind when I was doing the presentation. So one area that you can look into during your this week's winter school is accessibility, how these two technologies can be used in it, and immersive VR and AR, like rendering textures, with contact of virtual objects, and also navigation is one area. And also the other thing is training and rehab, social and emotional, music and media. So all these are exciting areas that you can probably think on creating. And also with electrical stimulation, that since we are not using this particular technology during this winter school, one thing exciting is how our kinesthetic or kinesthetic systems work. As I said before, there is this sensor network underneath our skins that detects these tactile sensors. And similarly, how our muscles work. For example, if I want to move my hand like this, my brain sends the signals into my muscles so that I can actuate my hands and joints. So we can also hack that system. So when you give these electrical pulses on top of your muscles, so the muscles would think that the signal came from the brain and it gets actuated. That's sort of how, in a very holistic way, how this muscle stimulation works. So we can use this particular hardware that you are using. I have one of the kits that we developed. If you are excited, I can probably try it out with you. So so this is also a technology that is being used, but we use it for some of the ongoing research work to render force feedback. So how it happens is when you try to push something, there are particular muscle groups that actuate, but because there's nothing physical, you cannot practically push it. But how we do is we co-actuate the opposite muscle group, so you feel some resistance when you try to push it. And so it's quite interesting. These are some of the demos. And yeah, so that's quite about it. I wanted to introduce the technologies today about the Vibro-tactile and Electro-tractile, and you can access the toolkits in GitHub in your development processes. And yeah, thank you.